Hello there, and welcome to our journey through the quiet corners of space. Tonight we will explore something extraordinary, something ancient, and something that is approaching us from the vast darkness between the stars. We are going to discover the story of an interstellar visitor that has traveled billions of years to reach our cosmic neighborhood. Not just another asteroid or comet from our solar system, but a true wanderer from the depths of space, carrying secrets from stellar nurseries that existed long before our Earth was born. We will explore the mysterious trajectory that brings this ancient traveler toward us and what its arrival might mean for our understanding of the cosmos. Before we begin, I would love to know where you are listening from tonight. Perhaps you are in a quiet room, maybe lying back with your eyes closed. No matter where you are, we share this moment together, floating on our small planet through the vastness of space. If you find these kinds of quiet explorations interesting, I would be grateful if you could subscribe or like this program. It helps this gentle signal reach other curious minds who might enjoy these peaceful journeys through science. Take a moment now to settle in. Let your thoughts slow down to match the patient rhythm of planetary orbits. Tonight, our exploration focuses on one of the most remarkable discoveries in recent astronomy, an object designated 3I/A Tels, racing toward us on what scientists call a death trajectory. This interstellar messenger carries within itself the story of distant worlds and ancient cosmic events, traveling faster than anything we have ever encountered in our local space. Far beyond the familiar glow of our sun and the vast darkness between the stars, something ancient has been drifting for billions of years. This traveler has witnessed the birth and death of countless suns, has felt the gravitational whispers of worlds we will never see, and has carried within its frozen heart the chemical signature of stellar nurseries that existed long before our Earth took shape. On a summer morning in July 2025, an astronomer at the Atlas Telescope facility in Chile noticed something unusual in their nightly observations. A faint point of light had appeared where none existed before, moving with purpose across the background stars. Within days, careful analysis revealed the extraordinary truth. This visitor had come from beyond our solar system, traveling faster than any object ever recorded in our cosmic neighborhood. Scientists named this Wanderer 3 I/A Tellus, marking it as the third confirmed interstellar object to grace our solar system with its presence. The designation carries profound meaning. The I stands for interstellar, indicating an origin in the space between stars. The 3 inches places it in the rare company of only 2 previous visitors, the enigmatic Oumuamua, discovered in 2017, and the comet Borisov, found in 2019. What makes 3I/Atlas remarkable extends far beyond its interstellar origins. Early measurements suggest this object may be older than our entire solar system. While our sun and planets formed approximately 4.5 billion years ago, this messenger appears to have been wandering the galaxy for 7 to 11 billion years. It carries within its structure the memory of a time when our corner of the universe looked entirely different. To understand the significance of this ancient traveler, we must first appreciate the emptiness from which it emerged. Interstellar space represents one of the most barren environments in the known universe. Between the stars, matter exists in such sparse concentrations that a volume the size of Earth might contain only a few atoms. The temperature hovers just a few degrees above absolute zero, creating conditions more extreme than anything we can replicate in terrestrial laboratories. Yet this apparent emptiness teems with subtle activity. Cosmic rays streak through the void at nearly the speed of light. Magnetic fields, stretched thin across vast distances, create invisible highways along which charged particles travel. Occasionally, stellar winds from distant suns push against this tenuous medium, creating bubbles and currents in the galactic environment. For billions of years, 3I/Atlas has navigated this hostile realm. The object has endured bombardment by high energy particles that would sterilize any known form of life. It has experienced temperature variations as it passed near different types of stars or through varying densities of interstellar matter. Each of these experiences has left subtle marks on its composition and structure, creating a record of cosmic history that we are only beginning to learn how to read. The physics that govern 3I/Atlas's journey operate on scales that challenge human comprehension. Moving at 58 kilometers per second relative to our sun, this object travels fast enough to circle Earth's equator in roughly 20 minutes. This velocity places it firmly in the realm of hyperbolic trajectories, meaning it possesses more than enough energy to escape the gravitational influence of our solar system entirely. Understanding hyperbolic motion requires us to think differently about cosmic relationships. Most objects in our solar system follow elliptical paths, bound by the sun's gravity in endless cycles of approach and recession. But 3I/Atlas follows a different law. Its trajectory resembles a hyperbola, a mathematical curve that approaches but never quite touches two invisible lines extending to infinity. This geometry reflects the object's fundamental nature as a visitor rather than a resident. The energy required to achieve such velocities speaks to violent processes in the object's past. Something, perhaps billions of years ago, accelerated this mass to interstellar speeds. The most likely scenario involves gravitational interactions during the formation of its parent planetary system. As planets coalesced around a distant star, their gravity would have scattered smaller objects in all directions. Some would have gained just enough energy to break free entirely, beginning journeys that would last for geological ages. Current estimates place 3I/Atlas's orbital eccentricity at 6.141 comma, making it the most extreme hyperbolic trajectory ever measured. To appreciate this number, consider that Earth's nearly circular orbit has an eccentricity close to zero, while highly elliptical comet orbits might reach values near 1. Anything above 1 indicates an unbound orbit, but 3I/Atlas's value of 6.141 represents motion so energetic that its path appears almost straight compared to the curved orbits of solar system natives. This extreme trajectory carries implications for the object's ultimate fate. After its brief passage through our solar system, 3I/Atlas will continue into the void, never to return. Its path will carry it away from our sun and toward other stars, though it will likely never approach another stellar system closely enough to be captured or significantly altered. In a sense, we are witnessing both the beginning and end of this object's story from our perspective. The age estimates for 3I/Atlas emerge from careful analysis of its likely origins within our galaxy. Astronomers have traced its trajectory backward, attempting to determine where it might have come from and when it began its journey. The calculations suggest it originated in the thick disk of the Milky Way, a region populated by older stars and different chemical compositions than our Sun's current neighborhood. Stars in the thick disk formed during the galaxy's more chaotic youth, when stellar collisions and gravitational interactions were more common. The heavy elements that make up rocky planets were less abundant then, creating planetary systems with different characteristics than those forming today. 3I/Ateles may represent a relic from this earlier epoch, carrying chemical signatures that reflect the galactic environment of billions of years past. The object's immense age also raises profound questions about the nature of time itself on cosmic scales. While human civilization spans mere thousands of years, and complex life on Earth has existed for hundreds of millions, 3I/Atlas has been traveling for periods that dwarf even these vast stretches. It began its journey when our galaxy was younger and more active, when many of the stars we see today had not yet formed. During its long voyage through space, 3I/Ateles has experienced cosmic history in ways we are only beginning to understand. It has felt the gravitational influence of our galaxy's central black hole, experienced the passage through spiral arms, where star formation proceeds at accelerated rates, and perhaps witnessed stellar explosions whose light has only recently reached Earth. The implications extend beyond mere age. This ancient wanderer carries information about conditions in parts of the galaxy we cannot directly observe. Its chemical composition reflects the stellar nursery where it formed, potentially revealing details about star formation processes that operated billions of years ago. Its physical structure may preserve evidence of cosmic ray bombardment, magnetic field interactions, and other phenomena that shaped the galactic environment across vast stretches of time. As 3/Atlas continues its approach toward our Sun, it provides us with an unprecedented opportunity to study materials and processes from the early galaxy. Each observation adds to our understanding of how planetary systems form and evolve, how objects move through interstellar space, and how the galaxy itself has changed over cosmic time. The discovery of this messenger from deep time reminds us of our place in a universe far older and more dynamic than previous generations could have imagined. We exist in a brief moment of cosmic history, observing phenomena that began long before our solar system existed and will continue long after our sun burns out. Yet through careful observation and analysis, we can reach across these impossible spans of time and space to touch something that remembers the galaxy's ancient past. In the coming months, as 3I/Atlas approaches its closest point to the Sun, we will have the chance to study this ambassador from deep time in unprecedented detail. What secrets might it reveal about the cosmic environment from which it emerged? What can its chemistry tell us about the stellar processes that operated when the universe was young? These questions drive our continued observation of this remarkable visitor. The story of 3I/Atlas speaks to the fundamental interconnectedness of cosmic phenomena. This object, born in circumstances we can barely imagine, has traveled across distances that reduce our largest telescopes to mere toys, carrying with it a record of processes and events that shaped the galaxy we call home. Its arrival in our solar system represents not just a scientific opportunity, but a profound reminder of the deep time that underlies all cosmic evolution. As we watch this ancient messenger continue its journey, we are witnessing more than just another astronomical phenomenon. We are seeing direct evidence of the galaxy's history, of the vast scales over which physical processes operate, and of the remarkable fact that information can be preserved and transported across such immense stretches of space and time. In 3I/A Tellus, we find not just a visitor from another star system, but a tangible connection to the deep past of our universe itself. At 58 kilometers per second, 3I/A Thales moves faster than any object ever recorded passing through our solar system. This velocity represents more than mere speed. It embodies the fundamental physics that govern motion on cosmic scales and reveals the extraordinary energies required to traverse the space between stars. To appreciate the significance of this measurement, consider that Earth orbits our Sun at approximately 30 kilometers per second, the fastest spacecraft humanity has ever launched. The Parker Solar Probe reaches speeds of nearly 200 kilometers per second when diving close to the Sun's surface. Yet even this technological achievement pales beside the natural velocity of our interstellar visitor, which maintains its breakneck pace through the sheer momentum accumulated over billions of years of travel. The physics underlying such motion begins with the concept of escape velocity, a fundamental threshold that determines whether objects remain bound to gravitational systems or break free into interstellar space. Every massive body creates a gravitational well, requiring specific amounts of energy to escape entirely. From Earth's surface, that threshold sits at approximately 11 kilometers per second. Our Sun demands 42 kilometers per second for complete escape from its gravitational influence. 3I/Atlas exceeds this solar escape velocity by a significant margin, marking it unambiguously as an interstellar intruder rather than a native of our cosmic neighborhood. But velocity alone tells only part of the story. The mathematical description of the object's motion requires understanding hyperbolic trajectories, paths that curve through space without ever closing into repeating loops. Most objects in our solar system follow elliptical orbits described by eccentricities between 0 and 1. Earth's nearly circular path has an eccentricity of approximately 0.01, 7, while highly elongated comet orbits might reach values near zero point 0.9. Once eccentricity exceeds unity, however, the trajectory becomes unbound, following curves that extend to infinity without repetition. 3I/A Tellus possesses an orbital eccentricity of 6.14, 1 comma, placing it in the extreme hyperbolic category. This value represents the most eccentric trajectory ever measured for any object in our solar system, indicating motion so energetic that the sun's gravity can barely deflect its path. Rather than following a closed curve, the object traces a hyperbola that approaches but never touches two straight lines extending infinitely in opposite directions. Such extreme values emerge from the interplay between kinetic energy and gravitational potential energy. Objects moving at exactly escape velocity possess zero total energy relative to their gravitational system. They can just barely break free, following parabolic paths that asymptotically approach zero velocity at infinite distance. 3I/AT-LAS, however, carries substantial excess energy, maintaining significant velocity even after escaping all gravitational influences. This excess energy reveals something profound about the object's history. The laws of physics dictate that energy cannot be created or destroyed, only transferred between different forms. The kinetic energy propelling 3I/A Tellus through space must have originated somewhere, imparted by some cosmic process that accelerated the object to its current velocity billions of years ago. The most likely scenario involves gravitational interactions during planetary system formation. As young planets grow through accretion of smaller bodies, their gravity scatters debris in all directions. Most of this material either falls into the growing planets or settles into stable orbits around the parent star. But occasionally, gravitational encounters provide just enough energy to accelerate objects beyond escape velocity, launching them on interstellar trajectories. Computer simulations of planetary formation suggest that every stellar system ejects substantial amounts of material during its formation phase. The process resembles a cosmic slingshot, with planetary gravity converting orbital energy into translational motion. Objects that receive particularly energetic kicks can achieve velocities sufficient for interstellar travel, beginning journeys that may last for billions of years. The specific velocity of 3I/Atlas provides clues about the nature of these ancient interactions. 58 kilometers per second represents a substantial energy boost, suggesting encounters with relatively massive objects or particularly favorable geometric arrangements. The object may have experienced multiple gravitational assists, accumulating velocity through a series of planetary encounters before finally achieving escape. Comparing 3I/Atlas with previous interstellar visitors reveals the diversity of possible launch mechanisms. Temu Mamua, the first confirmed interstellar object, moved at 26 kilometers per second relative to the Sun. Komet Borisov traveled at 32 kilometers per second. Each velocity represents a different history of gravitational interactions and energy transfer. The velocity distribution of interstellar objects reflects the statistical nature of planetary formation processes. Most ejected materials receive relatively modest energy boosts, creating a population of slow-moving interstellar wanderers. Fewer objects achieve intermediate velocities, while the highest speeds remain extremely rare. 3I/ALS represents the fast tail of this distribution, carrying energies that few objects ever achieve. Understanding these velocity relationships helps astronomers estimate the frequency of interstellar visits. Objects moving at higher speeds traverse any given region of space more quickly, reducing their likelihood of detection despite their greater abundance in interstellar space. The rarity of observed high-velocity visitors, like 3I/ATLAS, may reflect not their scarcity, but their brief residence times in observable regions. The hyperbolic nature of 3I/Atlas's trajectory also determines its future evolution through our solar system. Unlike elliptical orbits that bring objects back repeatedly, hyperbolic paths represent one-time encounters. The object approaches the Sun along one branch of its hyperbolic curve, reaches perihelion at the vertex, then recedes along the opposite branch, never to return. This geometric reality creates observational challenges for astronomers studying interstellar visitors. The objects remain visible for limited periods, constraining the time available for detailed analysis. 3I/Atlas was discovered in July 2025 and will disappear from observable range by early 2026, providing less than 2 years for comprehensive study. The timing of observations relative to perihelion passage affects what astronomers can learn about these visitors. As 3I/ATLAS approaches the Sun, solar heating will activate sublimation processes, creating the characteristic coma and tail that make comets visible. But the same heating that reveals internal composition also alters the object's structure, potentially destroying evidence of its interstellar journey. The extreme velocity of 3I/Atlas influences even basic measurements of its physical properties. Doppler shifts in reflected sunlight reveal the object's radial velocity component, while proper motion across the sky indicates transverse movement. Combining these measurements allows precise determination of the three-dimensional velocity vector, essential for tracing the object's trajectory backward through time. Such calculations require accounting for gravitational influences from all major solar system bodies. The Sun dominates the dynamics, but Jupiter's massive presence can significantly deflect incoming objects. Smaller planets contribute smaller but measurable effects, particularly for objects passing close to their orbits. Even asteroid gravitational influences become relevant for the most precise trajectory reconstructions. The mathematical complexity of these calculations reflects the chaotic nature of gravitational systems. Small uncertainties in initial conditions can lead to dramatically different outcomes over extended periods. This sensitivity limits astronomers' ability to determine exactly where 3I/Atlas originated or predict its precise future path after leaving our solar system. Nevertheless, statistical analyses provide valuable insights into the object's likely origins and destinations. By running thousands of trajectory simulations with slightly different initial conditions, astronomers can map probability distributions for the object's past and future locations. These studies suggest 3I/Atlas originated in the thick disk of our galaxy and will continue moving through the galactic halo for billions of years. The implications extend beyond individual objects to our understanding of galactic dynamics. Interstellar velocities reflect not only local gravitational interactions, but also the motion of stellar systems through the galaxy. Our Sun travels at approximately 200 kilometers per second relative to the galactic center, carrying the entire solar system along a complex orbit through the Milky Way. This motion creates relative velocity between our solar system and potential sources of interstellar objects. The observed velocity of 3I/ATLS represents the vector sum of its motion through space and our own galactic movement. Disentangling these components requires detailed modeling of galactic structure and dynamics, connecting small-scale observations to the largest scales of cosmic motion. The study of interstellar object velocities also provides unique probes of fundamental physics. The preservation of kinetic energy over billions of years of travel confirms our understanding of momentum conservation on cosmic scales. The precise trajectories followed by these objects validate our models of gravitational interactions and space-time geometry. As 3I/Atlas continues its passage through our solar system, its velocity remains the key parameter determining every aspect of the encounter. This single measurement connects the object to its ancient origins, governs its current trajectory, and determines its ultimate fate. In studying this velocity, we glimpse the fundamental forces that shape motion throughout the universe, from the smallest particles to the grandest cosmic structures. The legacy of 3I/Atlas will extend far beyond its brief visibility from Earth. Its record breaking velocity establishes new benchmarks for interstellar object studies, while its hyperbolic trajectory provides templates for understanding future visitors. Most importantly, its motion through our solar system demonstrates the dynamic nature of the galaxy, where matter flows constantly between stellar systems, carrying information across vast distances and connecting distant worlds through the universal language of orbital mechanics. Imagine holding a grain of sand that originated on a beach hundreds of millions of kilometers away, or breathing air that last circulated in an atmosphere orbiting a different star. While such direct contact with alien worlds remains beyond our reach, 3I/Atlas offers something almost as remarkable: a chemical sample from stellar systems that formed billions of years before our own sun ignited. The composition unveiled by spectroscopic analysis reveals an object unlike any comet born in our solar system, where typical solar system comets show water ice as their dominant volatile component. 3I/Atlas displays an unusually high concentration of carbon dioxide. This chemical signature provides a direct window into the conditions that prevailed during its formation in a distant stellar nursery. Carbon dioxide, molecular formula CO, represents one of the fundamental building blocks of planetary atmospheres and cometary nuclei throughout the universe. On Earth, this molecule drives climate patterns and supports photosynthesis in plants. In space, CO ice forms at temperatures around 148 Kelvin, considerably warmer than the conditions required for water ice formation. This temperature sensitivity makes carbon dioxide a valuable tracer of thermal conditions in forming planetary systems. The James Webb Space Telescope's initial observations of 3I/Atlas revealed an extraordinarily high ratio of carbon dioxide to water, among the highest ever recorded in any comet. This unusual chemistry suggests formation in an environment where carbon dioxide could condense and accumulate more readily than water ice, pointing to specific temperature and pressure conditions in the object's birthplace. Such chemical signatures emerge from the complex interplay of stellar evolution, planetary system formation, and the distribution of elements throughout the galaxy. When massive stars reach the end of their lives, they synthesize heavy elements in their cores and distribute them through space via supernova explosions. These stellar explosions enrich the interstellar medium with carbon, oxygen, silicon, and other elements essential for planet formation. The relative abundances of different elements vary both spatially and temporally throughout the galaxy. Regions closer to the galactic center, where stellar densities are higher, experience more frequent supernova enrichment and develop different chemical compositions than areas in the galactic suburbs, where our sun currently resides. Similarly, stellar systems that formed earlier in galactic history had access to different element ratios than those forming today. 3I/Atlas appears to have originated in the thick disk of the Milky Way, a region populated by stars considerably older than our sun. These stellar systems formed when the galaxy was younger and more chemically primitive, with lower abundances of heavy elements and different ratios of carbon to oxygen. The unusual chemistry of 3I/Atlas may reflect these ancient abundance patterns, preserved in ice that has remained essentially unchanged for billions of years. The process of carbon dioxide sublimation in 3I/ATLS reveals additional layers of chemical complexity. As the object approaches the sun and its surface temperature rises, frozen CO test transitions directly from solid to gas without melting, a process called sublimation. This phase change occurs at lower temperatures than water ice sublimation, meaning carbon dioxide begins outgassing while water remains frozen in the nucleus. Observations from multiple space based telescopes have tracked this sublimation process in real time, revealing how the comet's coma develops as solar heating penetrates deeper into the nucleus. The European Space Agency's Gemini South Telescope captured detailed images showing vast quantities of carbon dioxide streaming away from the nucleus, creating a diffuse atmosphere that extends for thousands of kilometers around the solid core. Alongside carbon dioxide, spectroscopic analysis has identified several other molecular species in 3I/AT-LAS's coma, cyanide, with the chemical formula CN appears prominently in the observations. While cyanide's reputation as a poison makes it seem sinister, this molecule commonly appears in comets as they approach the sun. The presence of cyanide actually reassures astronomers that 3I/AT-LAS behaves like a normal comet despite its exotic origins. The detection of water vapor, carbon monoxide, and carbonyl sulfide rounds out the known chemical inventory of 3I/AT-LAS. Each of these molecules provides additional constraints on formation conditions and evolutionary history. Water vapor indicates the presence of hazo ice in the nucleus, though in much lower concentrations than typical solar system comets. Carbon monoxide, extremely volatile and difficult to retain over long periods, suggests that portions of the nucleus have remained extremely cold throughout the object's interstellar journey. Carbonyl sulfide, with formula OCS, represents a more complex molecule whose presence implies specific chemical reactions during the comet's formation. This compound typically forms through interactions between carbon monoxide, hydrogen sulfide, and other species under particular temperature and pressure conditions. Its detection in 3I/AT-LAS provides clues about the chemical processes that operated in the object's birth environment. The unusual carbon dioxide dominance in 3I/AT. This may also reflect exposure to cosmic ray bombardment during its long interstellar journey. High energy particles streaming through space can break molecular bonds and create new chemical compounds through radiolysis. Over billions of years, such processes might alter the surface composition of interstellar objects, potentially explaining some of the chemical peculiarities observed in 3I/AT-LAS. Laboratory experiments attempting to simulate these processes have yielded intriguing results. When researchers expose ice mixtures to high energy radiation similar to cosmic rays, they observe the preferential destruction of water molecules and the relative preservation of carbon dioxide. This selective chemistry could explain why 3I/AT-LAS shows such high CO POTS concentrations, despite likely forming in environments where water ice was initially more abundant. The spatial distribution of different chemical species within the nucleus adds another layer of complexity to the compositional picture. As solar heating penetrates the surface layers, different molecules sublimate at different depths, creating chemical gradients within the escaping gas. Early observations suggest that carbon dioxide dominates the initial outgassing, followed by water vapor as heating reaches deeper into the nucleus. This layered structure may preserve a record of environmental changes during the object's formation. If conditions in the birth stellar system varied over time, different ice layers might record different chemical signatures. The ongoing sublimation of 3I/Atlas essentially provides a core sample through time, revealing how conditions evolved in a distant planetary system billions of years ago. The isotopic composition of the various molecules provides additional insights into formation processes and evolutionary history. Different isotopes of carbon, oxygen, and other elements trace distinct nucleosynthetic pathways in stellar interiors. The isotopic ratios measured in 3I/Atlas can potentially identify the types of stars that contributed material to its birth environment. Preliminary isotopic measurements suggest some similarities to solar system materials, but with subtle differences that reflect the object's exotic origins. The ratio of carbon 13 to carbon 12, for example, appears slightly elevated compared to typical solar system values. This enhancement might indicate formation in a region with different stellar populations or exposure to particular nucleosynthetic processes not common in our local galactic neighborhood. The detection of atomic nickel vapor in 3I/Atlas's coma represents another remarkable discovery. Nickel atoms typically remain bound in solid metal phases at the low temperatures characteristic of comet nuclei. Their presence in the gas phase suggests either unexpected heating mechanisms or unusual metal compounds that volatilize more readily than pure nickel metal. This metallic component may trace back to the earliest stages of planetary system formation, when metal-rich dust grains condensed from stellar winds and supernova ejecta. The incorporation of such materials into cometary nuclei provides direct samples of the dust that seeded planet formation in distant stellar systems. By analyzing the nickel and other metallic components, astronomers can probe the mineral chemistry of alien worlds. The ongoing evolution of 3I/Atlas's chemical signature as it approaches perihelion offers a unique opportunity to study how interstellar materials respond to solar heating. Unlike laboratory experiments that can only approximate cosmic conditions, this natural experiment provides real-time data on chemical processes operating under authentic space environment conditions. Different molecules exhibit distinct sublimation rates and gas phase chemistry as conditions change. The temporal evolution of the coma composition reveals which compounds are most susceptible to thermal processing and which remain stable under varying conditions. This information proves crucial for understanding how chemical information is preserved or modified during interstellar journeys. The chemical story of 3I/Atlas ultimately connects our solar system to the broader galactic ecosystem. The elements and compounds detected in this ancient visitor originated in stellar interiors, were processed through supernova explosions, condensed in protoplanetary disks, and survived billions of years of interstellar travel to reach our cosmic neighborhood. This chain of chemical evolution illustrates the cycling of matter through different phases of cosmic history. The carbon atoms, now sublimating from 3I/Atlas, may have been forged in the nuclear furnaces of massive stars that died before our sun was born. The oxygen molecules entering our solar system carry the chemical signature of stellar processes that operated under conditions very different from those that prevailed during our own planetary system formation. Each spectral line recorded by our telescopes represents a message from deep space and deep time written in the universal language of atomic and molecular physics. By decoding these chemical signatures, astronomers can reconstruct the environmental conditions that prevailed in distant stellar systems and trace the evolution of matter through cosmic history. As 3I/Atlas continues its journey toward perihelion, continued monitoring of its chemical evolution will provide unprecedented insights into the composition and behavior of interstellar materials. This ancient messenger carries within its frozen nucleus a direct sample of the galaxy's chemical evolution, offering a tangible connection to the cosmic processes that shape the universe on the largest scales. October 3rd, 2025, in the pre-dawn darkness above Chile's Atacama Desert, the Atlas South telescope has been tracking our visitor for 3 months now, recording its position against the background stars with mechanical precision. Tonight marks a significant milestone in 3I/Atlas's passage through our solar system, its closest approach to Mars, passing within 0.19 astronomical units of the red planet's orbit. This encounter represents more than a celestial coincidence. The gravitational choreography unfolding across millions of kilometers of space follows laws written into the very fabric of the universe, equations that govern the motion of everything from dust grains to galaxies. As 3I/Atlas sweeps past Mars, we witness a demonstration of orbital mechanics operating on a scale that dwarfs human experience, yet obeys the same principles that guide a thrown stone's arc through Earth's sky. The path that 3I/Atlas traces through our solar system resembles a gentle curve, almost imperceptible when viewed from the vast distances involved, yet precisely determined by the intricate balance between kinetic energy and gravitational influence. Unlike the closed ellipses followed by planets and most comets, this trajectory forms an open hyperbola, a mathematical shape that extends infinitely in both directions, never returning to its starting point. Understanding this path requires us to think in 3 dimensions, visualizing motion through space rather than across flat surfaces. 3I/Atlas approaches our solar system from roughly the direction of the constellation Lynx, moving at an angle to the plane where most planets orbit. This inclination means the object's trajectory cuts through our solar system like a tilted needle threading through a series of concentric circles. The precise geometry of this passage emerges from calculations that account for every significant gravitational influence, and Wang Sen dominates the dynamics, its massive presence bending the comet's otherwise straight path into the characteristic hyperbolic curve. But other bodies contribute their own subtle influences, creating perturbations that astronomers must carefully model to predict the object's future positions. Jupiter, with its enormous mass and relatively close approach to 3I/Atlas's path, exerts the most significant planetary influence. The giant planet's gravity will provide a slight acceleration to our visitor, adding energy to its already impressive velocity. This gravitational assist, similar to the techniques used by spacecraft engineers to boost probe speeds, will increase 3I/Atlas's departure velocity by several kilometers per second. The timing of these gravitational encounters follows a precise sequence determined by celestial mechanics. Mars comes first, on October 3rd, offering a relatively gentle interaction due to the red planet's modest mass. The effect remains barely measurable, shifting the comet's trajectory by mere fractions of a degree, but these small changes accumulate over cosmic distances. Following the Mars encounter, 3I Atellus continues inward toward its appointment with perihelion, the point of closest approach to our Sun. This moment, calculated to occur on October 29th, 2025, will bring the object to within 1.36 astronomical units of our star's surface. For comparison, this distance places the comet slightly farther from the Sun than Earth's orbit, ensuring it receives substantial solar heating without experiencing the extreme conditions that would vaporize its nucleus entirely. The approach to perihelion marks the most active phase of 3I/ATLAS's passage through our solar system. Solar radiation intensity increases as the inverse square of distance, meaning the object will receive nearly twice as much energy per unit area at perihelion compared to its current position. This heating will drive sublimation processes that transform the dormant nucleus into an active comet, complete with the characteristic tail and coma that make such objects visible to telescopes. The physics governing this transformation involve complex interactions between electromagnetic radiation and frozen materials. Solar photons penetrate the surface layers of the nucleus, depositing energy that raises temperatures above the sublimation points of various ices. Different compounds respond to heating at different rates, creating a temporal sequence of chemical evolution as the comet approaches and recedes from the Sun. Water ice, abundant in most solar system comets, sublimates at temperatures around 190 Kelvin when exposed to the vacuum of space. Carbon dioxide, unusually prominent in 3I/ATLAS, begins outgassing at significantly lower temperatures, around 148 Kelvin. This difference means AU-TALIS sublimation will commence well before the comet reaches perihelion, providing early indicators of internal composition. The geometry of the comet's approach determines which portions of its surface receive the most intense solar heating. As 3I/Atlas tumbles through space, different regions experience varying degrees of illumination, creating complex patterns of sublimation that contribute to the asymmetric development of its coma and tail. These structural details provide clues about the object's rotation state, surface composition, and internal structure. Beyond perihelion, 3I/8 will begin its journey outward through the outer solar system, gradually cooling as solar distance increases. The next significant encounter occurs on December 19th, 2025, when the comet passes closest to Earth at a distance of 1.8 astronomical units. This approach, while substantially closer than the Mars encounter, poses no threat to our planet due to the vast scales involved. The Earth encounter provides the optimal opportunity for detailed observations from our planet's surface and orbiting telescopes. At its closest approach, 3I/Atlas will appear brightest in Earth's skies, offering astronomers their best chance to study its composition, structure, and behavior in detail. Ground-based telescopes will work in coordination with space-based instruments to capture data across multiple wavelengths of light. The viewing geometry during Earth's closest approach favors observers in the northern hemisphere, where the comet will appear relatively high above the horizon during evening hours. Professional observatories worldwide were coordinating their efforts to maximize scientific return from this brief window of opportunity. Amateur astronomers with modest equipment may also glimpse this visitor from the depths of space. Following the Earth encounter, 3I/A Tellus continues its outward journey toward the outer planets. Jupiter's influence becomes increasingly significant as the comet approaches the giant planet's orbital region. The encounter with Jupiter, predicted for March 2026, represents the final major gravitational interaction before 3I/A Tellus leaves our solar system forever. Jupiter's massive gravitational field will accelerate the already fast-moving comet, adding several kilometers per second to its velocity through a process known as a gravitational slingshot. This additional energy boost ensures that 3I/Atlas will depart our solar system even faster than it arrived, carrying kinetic energy gained from its brief interaction with our star and planets. The mathematical precision required to predict these encounters reflects the deterministic nature of gravitational systems. Given perfect knowledge of initial conditions and all relevant forces, astronomers could, in principle, calculate the exact position of 3I/ATLAS at any future time. In practice, small uncertainties in measurements propagate through the calculations, creating growing uncertainty cones that limit prediction accuracy over extended periods. These uncertainties become particularly significant when tracing the object's trajectory backward through time, attempting to determine its origins in the galaxy. The chaotic nature of gravitational systems means that small errors in current measurements can lead to dramatically different reconstructions of the comet's past path. Nevertheless, statistical analyses provide valuable insights into the probable regions where 3I/ATLAS might have originated. Current calculations suggest the object likely began its interstellar journey somewhere in the thick disk of our galaxy, possibly in the direction of the constellation Gemini when traced backward through time. This origin region consists of older stellar populations with different chemical compositions than the Sun's current neighborhood, consistent with the unusual element ratios observed in the comet's composition. The path that brought 3I/ATLAS to our solar system required extraordinary precision in both direction and timing. Had the object arrived even slightly earlier or later, or approached from a different angle, it might have missed our solar system entirely, continuing its journey through interstellar space without offering us the opportunity to study a sample from distant worlds. This near-miss probability illustrates the rarity of interstellar encounters. The vast majority of objects ejected from other stellar systems never approach close enough to our Sun to become detectable with current technology. We observe only the tiny fraction that happen to pass through the relatively small sphere of space, where Earth-based telescopes can identify and track them. The trajectory of 3I/ATLAS also determines the long-term evolution of its orbit through the galaxy. After leaving our solar system, the object will continue moving through the sparse matter of interstellar space, gradually feeling the gravitational influence of our galaxy's spiral arms and central regions. Over millions of years, these large-scale forces will slowly modify its path, potentially bringing it near other stellar systems. The probability of 3I/Atlas ever encountering another star closely enough to be captured or significantly deflected remains extremely small. Interstellar space is so vast that even objects moving at high speeds typically travel for billions of years between close stellar encounters. Our visitor will likely spend the remainder of its existence in the cold darkness between stars, carrying with it the chemical signatures of its ancient birthplace. During its passage through our solar system, 3I/ATL serves as a messenger connecting different epochs of galactic evolution. Its trajectory links the ancient stellar nursery, where it formed billions of years ago, to our current cosmic neighborhood. By studying its path and properties, we glimpse the dynamic processes that shape matter transport throughout the galaxy. The gravitational interactions experienced by 3I/Atlas during its solar system passage will subtly alter its internal structure. Tidal forces from the sun and planets create stress patterns within the nucleus that could trigger structural changes or expose fresh material to space. These modifications add another layer to the comet's already complex evolutionary history. As we track 3I/ATLs along its predetermined path, we witness the unfolding of cosmic mechanics on their grandest scales. The same fundamental forces that shape atomic interactions and planetary motions also govern the trajectories of objects traveling between star systems. In following this ancient wanderer's journey through our cosmic neighborhood, we observe the universe's underlying unity, where physical laws operate consistently across scales ranging from the microscopic to the truly astronomical. The path through the void taken by 3I/Atlas represents more than mere celestial motion. It embodies the dynamic nature of our galaxy, where matter flows constantly between stellar systems, carrying information across vast distances and connecting disparate regions of space through the universal choreography of gravitational interaction. Each position along this trajectory tells part of a story that spans billions of years and countless light years, linking the deep past of galactic evolution to our present moment of observation and wonder. What happens when something that has slept for billions of years in the absolute cold of interstellar space suddenly feels the warmth of a star? For 3I/Atlas, this awakening began subtly, almost imperceptibly, as our sun's radiation first reached its ancient surface layers and began the slow process of transformation that would reveal the comet's hidden nature to telescopes across Earth. The awakening of a comet represents one of the most dramatic metamorphoses in the solar system. An object that appears as nothing more than a faint point of reflected sunlight gradually develops into a magnificent celestial display, sprouting tails that can stretch for millions of kilometers and creating glowing atmospheres larger than most planets. This transformation occurs not through any internal energy source, but through the patient work of electromagnetic radiation heating materials that have remained frozen for geological ages. Understanding this process requires us to consider the nature of the materials that compose cometary nuclei. These ancient bodies consist primarily of frozen volatiles compounds that exist as gases under terrestrial conditions, but remain solid in the extreme cold of space. Water ice dominates most solar system comets, but 3I/ATLS contains an unusual abundance of carbon dioxide ice, along with traces of carbon monoxide, methane, ammonia, and more complex organic molecules. Each of these substances possesses a characteristic sublimation temperature, the point at which it transitions directly from solid to gas without passing through a liquid phase. This process differs fundamentally from melting, which requires much higher pressures than exist in the near vacuum of space. As solar heating raises surface temperatures above these critical thresholds, different compounds begin outgassing in a sequence determined by their individual thermal properties. Carbon dioxide, abundant in 3I/Alas, begins sublimating at approximately 148 Kelvin when exposed to space vacuum. This temperature corresponds to conditions considerably warmer than the cosmic background radiation, but still far colder than Earth's polar regions. Water ice requires higher temperatures, around 190 Kelvin, while more volatile species like carbon monoxide begin outgassing at even lower temperatures. The initial stages of 3I/Atlas's awakening occurred while the comet remained beyond Mars's orbit, as increasing solar radiation began penetrating the outermost layers of its nucleus. Telescopic observations from this period revealed the first hints of activity, a barely detectable brightening that suggested the formation of a sparse coma around the previously dormant nucleus. This early coma consists primarily of carbon dioxide gas escaping from the nucleus surface, carrying with it microscopic dust particles embedded in the sublimating ice. The gas expands rapidly into the vacuum of space, creating a tenuous atmosphere that extends for thousands of kilometers around the solid core. While invisible to the naked eye, this nascent coma becomes apparent to sensitive instruments as it scatters and absorbs sunlight in characteristic patterns. The rate of coma development depends on several factors beyond simple solar heating. The rotation of the nucleus creates varying conditions across different regions of the surface, with areas facing the sun experiencing maximum heating while others remain in shadow. The thermal inertia of the nucleus materials determines how quickly temperatures rise in response to solar input, while the porosity and structure of the surface layers affect how efficiently heat penetrates into the interior. Early observations of 3I/Atlas revealed an asymmetric coma development, suggesting either an irregular nucleus shape or variations in surface composition. Some regions appeared more active than others, producing localized jets of gas and dust that contributed to the overall coma structure. These asymmetries provide valuable information about the internal heterogeneity of the nucleus and the distribution of different ice types within its structure. As solar heating intensifies during the approach to perihelion, the sublimation process accelerates dramatically. The coma grows both in size and brightness, becoming visible to increasingly modest telescopes. Spectroscopic analysis reveals the characteristic signatures of various molecular species escaping from the nucleus, providing direct information about the comet's composition and internal structure. The formation of a dust tail accompanies the development of the gas coma through a process that involves both gravitational and radiation pressure forces. Dust particles released during sublimation initially follow trajectories similar to the parent gas molecules, expanding radially outward from the nucleus. However, solar radiation pressure, while negligible for gas molecules, exerts significant force on microscopic dust grains. This radiation pressure acts like a gentle but persistent wind, pushing dust particles away from the sun along curved paths that depend on particle size, composition, and distance from the solar source. Larger particles experience less deflection than smaller ones, creating a size sorting effect that contributes to the structure and appearance of the developing dust tail. The interplay between gravitational forces and radiation pressure creates the characteristic curved shape of cometary dust tails. Unlike gas tails, which point almost directly away from the sun due to solar wind interactions, dust tails follow the comet's orbital path more closely, creating sweeping arcs that record the history of particle ejection over extended periods. Hubble's Space Telescope observations captured the early stages of tail formation in 3I/ATLAS, revealing delicate streamers of material extending from the nucleus in directions determined by the complex interplay of forces acting on particles of different sizes. These images provide unprecedented detail about the dust ejection process and the physical properties of the materials being released. The gas component of 3I/Atlas's coma exhibits its own distinctive behavior, driven primarily by interactions with the solar wind rather than radiation pressure. The solar wind, a stream of charged particles flowing constantly outward from the sun, creates an ionizing environment that strips electrons from neutral gas molecules escaping the comet nucleus. These newly created ions respond to magnetic fields embedded in the solar wind, causing them to flow almost directly away from the sun, regardless of the comet's orbital motion. This process creates the characteristic straight ion tail that points radially outward from the solar direction, often appearing blue due to fluorescence from ionized carbon monoxide molecules. The dual tail structure of active comets results from these different physical processes acting simultaneously on different components of the outgassing material. Dust tails preserve information about particle ejection over extended periods, while ion tails respond almost instantaneously to current solar wind conditions, creating a dynamic display that changes from day to day as space weather varies. For 3I/Atlas, the development of this dual tail structure provides unique insights into the behavior of interstellar materials under solar system conditions. The unusual chemical composition, particularly the high carbon dioxide content, creates spectroscopic signatures different from typical solar system comets, allowing astronomers to study how alien materials respond to our sun's influence. Temperature measurements of the developing coma reveal the thermal structure created by sublimation processes. Near the nucleus, where sublimation occurs most rapidly, temperatures can reach several hundred Kelvin despite the object's distance from the sun. This heating results from the energy released when solid materials transition to gas phase, a process that requires substantial amounts of thermal energy. Further from the nucleus, the expanding gas cools through adiabatic expansion, eventually reaching temperatures close to the ambient conditions of interplanetary space. This temperature gradient creates convection patterns within the coma that influence the distribution of different molecular species and affect the overall appearance of the developing tail structures. The awakening of 3I/Atlas also reveals information about the internal structure of its nucleus through the way heat penetrates beneath the surface. Thermal models suggest that significant temperature changes occur only in the outermost layers, extending perhaps a few meters into the nucleus interior. Deeper regions remain at nearly constant temperatures, preserving materials in pristine condition despite billions of years of cosmic ray bombardment. This layered structure means that ongoing sublimation essentially provides a core sample through the nucleus, exposing successively deeper materials as surface layers are stripped away. Different chemical signatures appearing at various stages of the awakening process may represent distinct formation epochs or environmental conditions from the comet's distant past. The rate of mass loss during the awakening phase can be substantial, with active comets losing tons of material per second during peak activity periods. For 3Z/Atlas, with its unusual composition and interstellar origins, this mass loss represents the irreversible destruction of materials that formed in alien stellar environments billions of years ago. Each molecule escaping into space carries with it chemical information about conditions in distant parts of the galaxy. Observations during the awakening phase also reveal the rotation state of the nucleus through periodic variations in brightness and gas production rates. As different regions of the surface rotate into and out of solar illumination, the overall activity level fluctuates in patterns that allow astronomers to determine rotation periods and axis orientations. The awakening of 3I/Atlas demonstrates the profound influence that stellar radiation can exert on materials that have remained dormant for cosmic ages. This process of thermal activation represents a fundamental mechanism by which energy flows through the universe, capable of triggering dramatic changes in objects that have traveled across vast distances and timescales. As the comet continues its approach toward perihelion, the awakening process will intensify, creating an increasingly spectacular display visible to telescopes worldwide. Each stage of this transformation provides new opportunities to study the composition and behavior of truly ancient materials, offering insights into the conditions that prevailed in distant stellar nurseries when our galaxy was young. The coma's awakening serves as a reminder of the dynamic nature of seemingly inert celestial objects, materials that appear stable and unchanging over human timescales can undergo dramatic transformations when subjected to the energy sources that pervade cosmic environments. In the case of 3I/Atlas, this awakening provides a unique window into the physical and chemical processes that govern the behavior of interstellar materials throughout the galaxy. Through careful observation of this awakening process, astronomers gain valuable insights into both the specific properties of our interstellar visitor and the general principles that govern comet behavior throughout the universe. Each photon of light scattered by the developing coma carries information about molecular processes, thermal dynamics, and the fundamental physics that shape the evolution of matter in cosmic environments. Somewhere in the constellation of Gemini, roughly 7,000 light years from where we sit today, lies a region of space that may have witnessed the birth of 3I/ATLS. This distant stellar neighborhood belongs to what astronomers call the thick disk of our galaxy, a realm populated by ancient suns that formed when the Milky Way itself was young and the universe looked fundamentally different than it does today. The thick disk represents one of the major structural components of our galaxy, distinct from the thin disk where our solar system currently resides. While the thin disk contains relatively young stars, like our Sun, along with most of the galaxy's current star formation activity, the thick disk harbors stellar populations that date back to earlier epochs of cosmic history. These regions preserve chemical signatures and stellar types that offer insights into the conditions that prevailed during the galaxy's formative years. Understanding the relationship between 3I/ATLS and its probable birthplace requires us to think like cosmic archaeologists, using the evidence preserved in this ancient visitor to reconstruct environments that existed billions of years ago. Just as terrestrial archaeologists piece together past civilizations from pottery fragments and tool remains, galactic archaeologists analyze the chemical compositions and orbital properties of stars and interstellar objects to understand how our galaxy evolved over time. The thick disk of the Milky Way extends several kiloparsecs above and below the galactic plane, forming a flattened but substantial structure that surrounds the thinner disk where most visible stars reside. This region contains stars with ages ranging from 8 to 12 billion years, making them among the oldest stellar populations in our galaxy. Their formation occurred during an era when the Milky Way was still assembling itself from smaller galactic building blocks. Chemical analysis of thick disk stars reveals compositions that differ significantly from stars in our solar neighborhood. These ancient stellar populations show lower abundances of heavy elements like iron, oxygen, and silicon, reflecting the fact that fewer generations of stars had lived and died to enrich the interstellar medium with the products of nuclear fusion. The relative ratios of different elements also differ, indicating that the mix of stellar masses and supernova types was different during the thick disk formation epoch. The unusual chemistry detected in 3A/Atelis appears consistent with formation in such an environment. The high carbon dioxide content and distinctive isotopic ratios suggest condensation from materials that had been processed through different stellar nucleosynthetic pathways than those that dominate our current galactic neighborhood. These chemical signatures serve as fingerprints that link our visitor to stellar populations and interstellar conditions that existed when the galaxy was significantly younger. Tracing the trajectory of 3I/A Talas backward through time provides additional clues about its origins. Computer simulations that account for the gravitational influences of stars, spiral arms, and the central galactic bulge suggest the object's path intersects the thick disk region several billion years ago. While the chaotic nature of galactic dynamics prevents precise determination of the exact birth location, statistical analyses point toward regions consistent with thick disk stellar populations. The formation environment that gave birth to 3I/Atlas likely differed dramatically from the conditions that prevailed during our solar system's formation 4.5 billion years ago. The earlier epoch saw more violent stellar interactions, higher rates of massive star formation, and different patterns of chemical enrichment. Supernovae occurred more frequently, injecting energy and heavy elements into the interstellar medium in ways that influenced the composition and structure of forming planetary systems. These ancient stellar nurseries also experience different physical conditions due to the galaxy's overall structure and dynamics. The thick disk formed during a period when the Milky Way was more compact and turbulent, with stellar orbits that carried objects through a wider range of galactic environments. Star formation occurred in molecular clouds with different temperatures, densities, and chemical compositions than those that characterize current star-forming regions. The planetary system that ejected 3I/A Talas into interstellar space likely formed around a star with properties characteristic of thick disk populations. Such stars typically show enhanced ratios of alpha elements like oxygen, magnesium, and silicon relative to iron, reflecting rapid chemical enrichment by massive stars that exploded as supernovae before intermediate mass stars could contribute significant amounts of iron through slower evolutionary processes. This chemical environment would have influenced the composition of dust grains and gas from which comets like 3I/A Talas condensed. The available raw materials contain different ratios of carbon to oxygen, different abundances of volatile compounds, and different mineral compositions than the materials from which solar system objects formed. These differences explain the distinctive chemical signatures observed in our interstellar visitor. The process by which 3I/Atellus was ejected from its birth system also reflects the violent dynamics common in early galactic environments. Planetary formation in the thick disk epoch occurred under conditions where stellar encounters and gravitational perturbations were more frequent than in the current galactic environment. These interactions increased the likelihood that small bodies would be scattered to high velocities, beginning the long journeys that characterize interstellar objects. Studying the thick disk through direct observation remains challenging due to the large distances involved and the faint nature of these ancient stellar populations. Most thick disk stars are too distant and dim to permit detailed spectroscopic analysis with current technology. The arrival of 3I/Atlas provides a rare opportunity to study material that originated in these remote regions, offering insights that would be difficult or impossible to obtain through traditional astronomical observations. The age of 3I/Ate, estimated at 7 to 11 billion years, places its formation during the peak epoch of thick disk star formation. This timing coincides with a period when the galaxy was still accreting smaller stellar systems and experiencing high rates of stellar birth and death. The chemical and dynamical conditions during this era shaped the properties of planetary systems in ways that continue to influence objects like our visitor, even after billions of years of interstellar travel. The stellar populations of the thick disk also help explain the high velocity of 3I/Atlas relative to the current solar system. Stars in the thick disk follow orbital paths that carry them to greater heights above the galactic plane and result in higher velocity dispersions compared to thin disk populations. When planetary systems in these environments eject objects into interstellar space, the resulting velocities reflect both local gravitational interactions and the broader galactic motion of the parent system. Comparing 3 Welles/Adialis with other interstellar visitors provides additional context for understanding thick disk environments. The three confirmed interstellar objects detected so far, Menomonowa, Borisov, and 3 As/Adialis, show distinct properties that likely reflect different formation environments and ejection mechanisms. These variations suggest that interstellar space contains a diverse population of objects that sample different epochs and regions of galactic evolution. The discovery of 3I/Atlas also raises questions about the frequency of interstellar visitors and their relationship to different galactic populations. Objects originating from thick disk systems must travel greater distances on average to reach our current location, reducing their local space density compared to objects from nearby thin disk systems. The fact that we have detected such an object suggests that the thick disk may have been a prolific source of interstellar material during its formation epoch. The chemical evolution of the thick disk proceeded through processes that differ from those operating in current star-forming regions. Early supernova explosions injected large amounts of energy into the interstellar medium, creating superbubbles and driving galactic fountain flows that redistributed material between different regions. These energetic processes influence the mixing of chemical elements and the thermal structure of molecular clouds where planetary systems form. The magnetic field structure in thick disk regions also differs from current galactic conditions, potentially affecting the formation and evolution of planetary systems during that epoch. Stronger magnetic fields could have influenced the collapse of molecular cloud cores, the accretion of material onto forming stars, and the dynamics of circumstellar disks where planets and comets condensed. Understanding the thick disk environment helps place 3I/A Tellus in the broader context of galactic evolution and stellar system formation. This ancient visitor represents not just a curiosity from interstellar space, but a sample of materials and processes that operated during a fundamentally different phase of cosmic history. Its chemical composition, physical properties, and orbital characteristics all carry information about conditions that prevailed when the galaxy was younger and more active. The ongoing study of 3I/Atlas will continue to provide insights into thick disk environments as the comet approaches perihelion and becomes more active. Detailed spectroscopic observations will reveal additional chemical species and isotopic ratios that constrain formation conditions. These measurements will contribute to our understanding of how chemical evolution proceeded in different galactic environments and how the diversity of stellar systems has changed over cosmic time. As we observe this messenger from the galaxy's edge, we are essentially conducting an archaeological excavation across space and time. Each measurement adds to our reconstruction of ancient environments, stellar populations, and chemical processes that shaped the Milky Way during its formative years. The echoes from distant regions and earlier epochs, preserved in the ice and rock of 3I/A Tellus, provide a direct connection to aspects of galactic history that would otherwise remain beyond our observational reach. Through careful analysis of this ancient wanderer, astronomers are learning to read the chemical signatures that encode information about stellar populations, planetary system formation, and galactic evolution. These insights enhance our understanding of how the current structure and composition of the Milky Way emerged from earlier, more chaotic conditions, and how objects like 3I/ATLAS serve as time capsules that preserve evidence of cosmic processes operating on the grandest scales of space and time. Understanding the trajectory of 3I/Atlas requires extending Kepler's laws beyond their original application to bound elliptical orbits. While planets and most comets follow closed elliptical paths that bring them back repeatedly to the same regions of space, interstellar objects trace open hyperbolic curves that represent one-time passages through gravitational systems. These hyperbolic trajectories obey the same underlying physics as elliptical orbits, but exhibit fundamentally different geometric properties. Every object in the universe that possesses mass attracts every other object through the fundamental force of gravity, creating a cosmic choreography that has been unfolding since the beginning of time. For 3I/A Telos, this dance manifests as a precisely determined trajectory through our solar system, governed by mathematical laws that were first described by Johannes Kepler 4 centuries ago and later refined by Newton's universal theory of gravitation. The elegance of orbital mechanics lies in its universality. The same equations that describe a satellite orbiting Earth also govern the motion of planets around stars, stars around galactic centers, and interstellar visitors like 3I/A Tellus passing through alien stellar systems. This mathematical unity reflects the fundamental nature of gravitational force, which acts across all scales of the universe with unwavering consistency. For elliptical orbits, the total energy is negative, indicating that the object lacks sufficient kinetic energy to escape the gravitational system entirely. Parabolic trajectories correspond to exactly zero total energy, representing the boundary case where an object has just enough velocity to escape to infinite distance. Hyperbolic trajectories, like that of 3I/Atlas, possess positive total energy, indicating motion energetic enough to maintain significant velocity even after escaping all gravitational influences. The mathematical description of 3I/Atalas's path begins with the concept of orbital energy, a quantity that remains constant throughout the object's journey through our solar system. This total energy consists of two components: kinetic energy associated with the object's motion and gravitational potential energy that depends on its distance from the sun. The sum of these energies determines whether the trajectory will be bound or unbound. The extreme hyperbolic nature of 3I/Atlas's orbit becomes apparent when we examine its orbital eccentricity, a parameter that describes how elongated the trajectory is compared to a perfect circle. Circular orbits have eccentricity 0, while highly elongated ellipses approach eccentricity 1. Parabolic escape trajectories have eccentricity exactly equal to 1, while hyperbolic trajectories exceed this value. 3I/Atlas possesses an orbital eccentricity of 6.141, placing it far into the hyperbolic regime and making it the most extreme trajectory ever measured for any object in our solar system. This value indicates motion so energetic that the sun's gravity barely deflects the object's path from a straight line. The mathematical implications of such extreme eccentricity affect every aspect of the trajectory calculation and observation planning. The velocity of 3I/Atlas at any point along its trajectory can be calculated using the vis-viva equation, a fundamental relationship that connects orbital velocity to position and orbital energy. This equation reveals that hyperbolic objects maintain substantial velocities even at large distances from the central body, unlike elliptical orbits, where velocity approaches zero at the farthest points from the sun. At its current distance from the sun, 3I/Atalas travels at approximately 58 kilometers per second, a velocity that will decrease slightly as it approaches perihelion due to the conversion of kinetic energy into gravitational potential energy. However, the object will regain this velocity during its outbound journey, ensuring that it departs our solar system with essentially the same speed it had upon arrival. The gravitational influence of planets modifies this simple two-body trajectory through what are known as perturbations. Jupiter, with its enormous mass and proximity to 3I/Atlas's path, exerts the most significant planetary influence on the comet's trajectory. These perturbations can be calculated using numerical integration methods that account for the gravitational effects of all major solar system bodies simultaneously. The Jupiter encounter, scheduled for March 2026, will provide 3I/Atlas with a gravitational slingshot effect, adding several kilometers per second to its departure velocity. This acceleration occurs because Jupiter moves through space at approximately 13 kilometers per second in its orbit around the Sun. When 3I/Atlas approaches Jupiter from behind and receives a gravitational acceleration, it gains energy from the planet's orbital motion. This energy transfer illustrates a fundamental principle of celestial mechanics. Gravitational encounters can redistribute energy between objects without violating conservation laws. Jupiter loses a tiny amount of orbital energy during the encounter, causing an immeasurable reduction in its orbital velocity, while 3I/A Talas gains this energy and departs with increased speed. The timing of gravitational encounters can dramatically affect their outcomes. Small changes in the arrival time or approach geometry can lead to significantly different departure trajectories and velocities. This sensitivity to initial conditions reflects the chaotic nature of gravitational systems, where tiny perturbations can grow into large differences over extended periods. The precise calculation of such gravitational encounters requires sophisticated mathematical techniques that account for the three-dimensional nature of the interaction and the relative motions of all involved bodies. Computer simulations model these encounters by solving systems of differential equations that describe how gravitational forces change the velocity vectors of the interacting objects over time. For 3S/Atelis, the specific geometry of its Jupiter encounter will determine not only its final departure velocity, but also its ultimate trajectory through the galaxy after leaving our solar system. The added energy from the gravitational slingshot will carry the object to greater distances and potentially different galactic regions than would have been possible without the encounter. Kepler's second law, which states that objects sweep out equal areas in equal times, applies to hyperbolic trajectories just as it does to elliptical orbits. This law explains why 3I/Atelas will move most rapidly during its perihelion passage and more slowly at larger solar distances. The area sweeping relationship provides a geometric interpretation of angular momentum conservation, one of the fundamental symmetries underlying orbital mechanics. The third of Kepler's laws, relating orbital periods to semi-major axes, requires modification for hyperbolic trajectories, since these paths do not have finite periods. Instead, the relationship extends to describe the time required to travel between different points along hyperbolic orbits, providing tools for predicting when 3I/A will reach specific locations during its solar system passage. The mathematical prediction of long-term trajectories becomes increasingly uncertain as time progresses due to the accumulation of small uncertainties in initial measurements. This limitation affects our ability to determine exactly where 3I/Atlas originated, or where it will travel after leaving our solar system. Nevertheless, statistical analyses provide valuable insights into the probable past and future evolution of the object's galactic orbit. The study of 3I/Atlas's orbital mechanics provides insights that extend beyond the specific case of this interstellar visitor. Understanding how objects move through gravitational systems helps astronomers interpret observations of exoplanetary systems, stellar clusters, and galactic dynamics. The mathematical tools developed for trajectory analysis apply across all scales of cosmic structure. The precision required for accurate orbital predictions reflects the deterministic nature of gravitational systems under Newtonian mechanics. Given perfect knowledge of initial conditions and all relevant forces, the future evolution of any gravitational system can in principle be calculated with arbitrary accuracy. In practice, measurement uncertainties and computational limitations restrict the precision of long-term predictions. Advanced orbital mechanics calculations for 3I/Ateles must also account for relativistic effects, though these remain small compared to classical gravitational influences. Einstein's theory of general relativity predicts subtle modifications to orbital behavior that become measurable only for the most precise observations. These effects include gravitational time dilation and the precession of orbital planes due to the curvature of spacetime near massive objects. The orbital mechanics of 3I/Atlas also demonstrate the role of conservation laws in determining cosmic behavior. Energy conservation ensures that the total energy remains constant throughout the trajectory, while angular momentum conservation governs the area sweeping behavior described by Kepler's second law. These conservation principles provide powerful constraints that simplify complex multi-body calculations. The trajectory of 3I/Atlas through our solar system represents a solution to the gravitational three-body problem, one of the most famous challenges in classical mechanics. While no general analytical solution exists for systems involving more than two gravitating bodies, numerical integration techniques provide accurate approximations that enable precise trajectory predictions over reasonable timescales. The dance of orbital mechanics, revealed by 3I/Atlas, connects our local solar system to the broader galactic environment through the universal language of gravitational interaction. The same physical laws that govern the comet's passage through our cosmic neighborhood also determine the motions of stellar systems throughout the galaxy, creating patterns and structures that persist across vast ranges of space and time. As 3I/Atlas continues its choreographed passage through our solar system, each position along its trajectory represents the outcome of gravitational forces operating with mathematical precision. The beauty of orbital mechanics lies not only in its predictive power, but in its revelation of the underlying order that governs motion throughout the cosmos. The legacy of studying 3I/Atlas's orbital mechanics will extend far beyond our current observations. The trajectory analysis techniques developed for this interstellar visitor will prove valuable for future encounters with similar objects, while the insights gained about hyperbolic orbits will enhance our understanding of how matter moves between stellar systems throughout the galaxy. Through the mathematical lens of orbital mechanics, we see 3I/Atlas not merely as a visitor from distant space, but as a participant in the grand cosmic ballet that has been unfolding since the universe began. Its trajectory through our solar system represents a brief moment in an eternal dance governed by the fundamental forces and conservation laws that shape the architecture of the cosmos on every scale. August 15th, 2025, at the European Southern Observatory's Very Large Telescope Complex in Chile's Atacama Desert. Four 8-meter mirrors work in unison through the pre-dawn hours, their adaptive optics systems compensating for atmospheric turbulence as they track a faint point of light moving slowly against the stellar background. This coordinated effort represents just one node in a global network of telescopes focused on extracting every possible photon from our interstellar visitor as it approaches its closest encounter with our Sun. The challenge of observing 3I/Ateles illustrates the remarkable ingenuity that astronomers have developed for studying the most distant and elusive objects in the universe. Each photon that reaches our telescopes after its journey from the comet carries information encoded in its wavelength, polarization, and arrival time. By analyzing these subtle signals, observers can determine composition, structure, rotation, and activity levels of an object millions of kilometers away. The discovery of 3I/Atlas itself exemplifies the power of automated survey systems designed to detect transient and moving objects across vast areas of sky. The Atlas survey, operating from stations in Hawaii and South Africa, uses relatively modest telescopes equipped with large field cameras to monitor the entire accessible sky every few nights. This systematic approach enables the detection of asteroids, comets, and other objects whose positions change noticeably between observations. When Atlas first detected 3I/Atlas on July 1st, 2025, the object appeared as nothing more than a faint dot that had moved slightly relative to background stars. The automated detection algorithms that flagged this movement use sophisticated pattern recognition techniques to distinguish genuine celestial objects from image artifacts, cosmic rays, and other sources of false signals. Only after confirming the object's reality through multiple observations could astronomers begin the process of determining its nature and origin. The initial characterization of any newly discovered object requires precise measurements of position and brightness over extended periods. For 3I/Atlas, these early observations revealed motion consistent with a highly eccentric orbit that could not be reconciled with any known solar system object. The trajectory calculations that identified the comet as an interstellar visitor required weeks of careful analysis and confirmation by multiple independent observers. Once 3I/Atlas's interstellar nature became apparent, astronomical priorities shifted toward maximizing the scientific return from this rare visitor. Telescopes worldwide began coordinated observations designed to characterize the object's physical properties, chemical composition, and activity levels. This international cooperation reflects the understanding that interstellar objects provide irreplaceable opportunities to study materials from distant stellar systems. The Hubble Space Telescope, with its location above Earth's atmosphere and exceptional optical quality, provides crucial observations impossible to achieve from ground-based facilities. Hubble's images of 3I/Atlas reveal details about coma structure, dust production rates, and nucleus properties that would be severely compromised by atmospheric blurring. The Space Telescope's ultraviolet capabilities prove particularly valuable for detecting specific molecular species that emit strongly at these shorter wavelengths. Hubble observations also enable precise measurements of the comet's size through techniques that analyze how sunlight reflects from the nucleus surface. These measurements require careful modeling of the object's rotation, shape, and surface properties to extract meaningful size estimates from brightness variations. Current analyses suggest a nucleus diameter between 300 meters and 5.6 kilometers, with a large uncertainty reflecting the challenges of determining sizes for such distant objects. The James Webb Space Telescope brings unprecedented infrared capabilities to the study of 3I/Atlas, operating at wavelengths where many molecular species display characteristic absorption and emission features. Webb's spectroscopic observations reveal the detailed chemical composition of gases escaping from the nucleus as solar heating drives sublimation processes. These measurements provide direct information about the materials that condensed in alien stellar systems billions of years ago. Webb's infrared sensitivity also enables measurements of thermal emission from the nucleus and coma, providing information about temperature distributions and heating mechanisms. These observations help astronomers understand how efficiently solar radiation penetrates into the nucleus interior and drives the observed gas and dust production. The thermal data complement visible light observations to create comprehensive models of the comet's structure and activity. Ground-based telescopes contribute essential observations that space-based facilities cannot provide, particularly long-term monitoring programs that track changes in activity levels over extended periods. Large optical telescopes, equipped with modern CCD cameras and spectrographs, can achieve sensitivities comparable to space telescopes for many types of observations while offering greater flexibility in scheduling and instrument configurations. The coordination between different observational facilities requires careful planning to ensure that complementary data sets are obtained simultaneously. Spectroscopic observations revealing chemical composition work synergistically with photometric measurements of brightness variations, while polarization studies provide information about dust grain properties that enhance interpretation of thermal observations. Radio telescopes contribute unique capabilities for detecting specific molecules through their rotational transitions at radio wavelengths. These observations prove particularly sensitive to carbon monoxide, hydrogen cyanide, and other species that may be difficult to detect at optical wavelengths. Radio observations also provide velocity information about gas motions within the coma through Doppler shift measurements. The challenge of observing 3 Or/Ateles varies dramatically as the comet's distance and activity level change throughout its solar system passage. During the early phases when the object remained distant and inactive, observations required the largest telescopes and longest exposure times to detect any signal above background noise levels. As solar heating increases activity and the comet develops a prominent coma, smaller telescopes become capable of useful observations. This evolution in observational requirements affects the allocation of telescope time and the types of measurements that are feasible at different epochs. Early observations focus on basic characterization of trajectory and size, while later observations during peak activity emphasize detailed spectroscopy and coma structure analysis. The brief window of optimal observing conditions requires careful coordination to maximize scientific productivity. Atmospheric conditions at observing sites become crucial factors in determining the quality of ground-based observations. The high altitude, dry conditions at major observatory sites like Mauna Kea in Hawaii and the Atacama Desert in Chile provide superior atmospheric transparency and stability compared to sea level locations. These conditions prove particularly important for spectroscopic observations that require precise wavelength calibration. Advanced instrumentation at modern telescopes incorporates numerous technologies designed to overcome observational challenges. Adaptive optics systems use deformable mirrors to correct for atmospheric turbulence in real time, enabling ground-based telescopes to achieve image quality approaching the theoretical diffraction limit. These systems prove particularly valuable for observations of extended objects like comet comas, where spatial resolution affects the ability to distinguish different structural components. Spectroscopic observations of 3I/A Talis require sophisticated techniques to separate the weak comet signal from much brighter sky background emissions. Modern spectrographs incorporate advanced detector technologies and data reduction algorithms that can extract meaningful spectra even when the target object contributes only a small fraction of the total recorded light. These capabilities enable detailed chemical analysis of objects that would have been undetectable just decades ago. The temporal aspects of observing 3 of the slash Atelas create additional challenges related to the comet's motion across the sky and its changing distance from Earth. Tracking telescopes must continuously adjust their pointing to follow the object's motion, while exposure times and observing strategies must account for the varying brightness as distance and activity levels change. These factors require careful coordination between different observational programs. Data reduction and analysis for 3I/Atlas observations involve complex procedures designed to extract maximum information from limited photon counts. Modern CCD and infrared detector systems produce digital images and spectra that require extensive processing to correct for instrumental effects, calibrate wavelength and flux scales, and remove contamination from cosmic rays and other sources. The statistical nature of photon detection means that observations of faint objects like 3I/Atlas are inherently limited by photon noise, which decreases as the square root of exposure time. This relationship drives observers to obtain the longest possible exposures while balancing against other factors like atmospheric stability and telescope scheduling constraints. Collaborative networks of professional and amateur observers contribute to the comprehensive monitoring of 3I/ATLAs throughout its passage. Amateur astronomers with advanced equipment can provide valuable photometric observations and imaging that complement professional observations, particularly for monitoring brightness variations and structural changes in the coma over time scales that professional facilities cannot continuously cover. The interpretation of 3I/Atlas observations requires sophisticated modeling techniques that combine physical theory with numerical simulations. Understanding how solar heating drives sublimation, how gas and dust interact with solar radiation, and how these processes create the observed coma and tail structures requires complex codes that solve the relevant physics equations under appropriate boundary conditions. Each observational technique contributes unique information that enhances our understanding of 3I/Atlas when combined with other measurements. Photometry reveals brightness changes that indicate activity variations and rotation properties. Spectroscopy provides chemical composition and gas production rates. Polarimetry yields information about dust grain sizes and shapes. Together, these diverse observations create a comprehensive picture of our interstellar visitor. The observational campaign for 3I/ATLAS represents a remarkable demonstration of how modern astronomy extracts detailed information about distant objects through careful analysis of electromagnetic radiation. Every photon carries information across vast distances of space, and the sophisticated techniques developed by astronomers enable the extraction of this information to reveal the properties of objects that would otherwise remain forever mysterious. As 3I/ATLAS continues its passage through the solar system, the ongoing observational campaign will provide unprecedented insights into the composition and behavior of interstellar materials. These observations not only advance our understanding of this specific object, but also develop techniques and establish benchmarks that will prove valuable for studying future interstellar visitors. The legacy of observing 3I/Atlas will extend far beyond the immediate scientific results. The observational techniques refined during this campaign, the international coordination mechanisms developed, and the insights gained about interstellar object properties will prepare the astronomical community for future encounters with similar objects. Each visitor from interstellar space provides a unique laboratory for studying materials and processes that operated in distant stellar systems, and our ability to extract maximum information from these brief encounters continues to improve with each new discovery. If Earth represented the size of a marble, the distance to the nearest star would stretch across a continent, and the space between stellar systems would contain vast emptiness, punctuated only rarely by wandering objects cast out from distant worlds. In this immense cosmic ocean, the detection of even 3 interstellar visitors within less than a decade represents an extraordinary convergence of cosmic timing and human technological capability. 3I/Atlas joins a select family of confirmed interstellar objects that have graced our solar system with their presence since systematic sky surveys began detecting these rare wanderers. Each member of this cosmic family tells a different story about planetary system formation, stellar evolution, and the processes that scatter materials between the stars. Together, they provide our first direct samples of matter from alien worlds and insights into the diversity of environments that exist throughout the galaxy. The first confirmed interstellar visitor, designated Oumuamua, captured worldwide attention when it was discovered on October 19th, 2017, by the Pan-STARRS telescope in Hawaii. This elongated object, roughly 400 meters in length, exhibited properties unlike anything previously seen in our solar system. Its highly reflective surface, unusual shape, and most notably, its unexpected acceleration away from the sun created a scientific mystery that persists to this day. Oumuamua's acceleration posed a fundamental puzzle because it occurred in a direction that could not be explained by gravitational forces alone. The acceleration was too small to result from rocket-like outgassing of volatile materials, yet too large to ignore in trajectory calculations. Various explanations have been proposed, including solar radiation pressure acting on an unusually thin structure, outgassing of hydrogen or other exotic materials, or even more speculative possibilities involving magnetic fields or non-gravitational forces. The mystery of Oumuamua's acceleration highlights how much we still don't understand about the objects that wander between stars. Its brief passage through our solar system provided limited opportunities for detailed study, and the object faded from telescopic visibility before definitive answers could be obtained. This first interstellar visitor established the importance of rapid response capabilities for future encounters with similar objects. The second confirmed interstellar visitor, 2I/Borisov, discovered by Crimean amateur astronomer Gennady Borisov on August 30th, 2019, presented a dramatically different character from its predecessor. Unlike the enigmatic Oumuamua, Borisov behaved exactly like a typical solar system comet, developing a prominent coma and tail as it approached the sun and displaying spectroscopic signatures consistent with familiar cometary materials. Borisov's familiar behavior provided reassurance that interstellar objects could indeed behave according to established comet physics, suggesting that Oumuamua's unusual properties represented an exception rather than the norm. The composition of Borisov, dominated by water ice and showing carbon monoxide abundances similar to solar system comets, indicated formation in an environment not dramatically different from the conditions that prevailed during our own planetary system's formation. The nucleus of 2I slash Borisov measured approximately 1 kilometer in diameter, similar in size to many short period comets that regularly visit the inner solar system. Its rotation period of approximately 7.5 hours and its gas production rates all fell within ranges observed for native solar system comets. This normalcy proved almost as scientifically valuable as Oumuamua's strangeness, establishing baseline expectations for interstellar comet behavior. Now 3I/Atlas provides a third perspective on the population of objects wandering between the stars, exhibiting properties that distinguish it from both previous visitors while sharing characteristics with each. Like Oumuamua, 3I/Atlas displays highly unusual composition and extreme orbital properties that set it apart from typical solar system objects. Like Borisov, it behaves as a recognizable comet, developing coma and tail structures through familiar sublimation processes. The orbital characteristics of these three visitors reveal the diversity of ejection mechanisms and subsequent evolutionary paths that shape the interstellar object population. Oumuamua arrived with a relatively modest velocity of 26 kilometers per second relative to the Sun, suggesting ejection from a planetary system through relatively gentle gravitational interactions. Its trajectory carried it through the inner solar system at a steep angle to the planetary orbital plane. Borisov approached at 32 kilometers per second, indicating somewhat more energetic ejection processes while still representing a velocity typical of gravitational scattering scenarios. Its orbital inclination was less extreme than Oumuamua's, bringing it closer to the plane where most planets orbit. The comet's long orbital period in its birth system, estimated at several million years, suggests formation in the outer regions of a distant stellar system. 3I/Atlas surpasses both previous visitors in terms of orbital extremes, with its velocity of 58 kilometers per second, representing the fastest interstellar motion ever recorded. Its orbital eccentricity of 6.141 indicates the most energetic trajectory observed, suggesting ejection through particularly violent processes or acceleration by multiple gravitational encounters. These extreme properties place 3I/Atlas at the high-energy tail of the interstellar object population. The size estimates for these three objects span a considerable range, reflecting both actual diversity and the challenges of determining dimensions for such distant targets. Oumuamua's elongated shape, an estimated length of 400 meters, made it the largest of the three, though its unusual geometry complicates size comparisons. Borisov's roughly spherical nucleus measured approximately 1 kilometer in diameter, while 3I/Atlas falls somewhere between these extremes, with diameter estimates ranging from several hundred meters to several kilometers. The composition differences between these interstellar visitors provide insights into the diversity of materials that exist in different stellar systems and ejection environments. Oumuamua's high reflectivity and lack of observable cometary activity suggested either unusual composition or depletion of volatile materials through processing during its interstellar journey. The absence of detectable outgassing made chemical analysis extremely difficult. Borisov's familiar composition, dominated by water ice with carbon monoxide concentrations similar to solar system comets, indicated formation under conditions resembling those in our own stellar neighborhood. The isotopic ratios measured in Borisov's coma showed subtle differences from solar system materials, but remained within expected ranges for objects formed around different types of stars. 3I/Atlas exhibits the most extreme composition yet observed, with carbon dioxide dominating over water ice to an unprecedented degree. This chemical signature suggests formation under conditions significantly different from those that characterized either our solar system or Borisov's birth environment. The unusual isotopic ratios and presence of complex molecules like carbonyl sulfide point to formation in stellar systems with different chemical abundances and thermal histories. The statistical rarity of these detections emphasizes how fortunate we are to observe even 3 interstellar visitors within such a short time period. Conservative estimates suggest that several interstellar objects larger than 100 meters in diameter should be present within our solar system at any given time, but most remain undetectable due to their faintness and rapid motion through the inner regions where our telescopes operate. The detection bias toward larger, more active objects means that the 3 confirmed interstellar visitors likely represent the most observable members of a much more diverse population. Smaller objects, inactive objects, or those following trajectories that don't bring them close to the sun remain beyond our current detection capabilities. Future survey telescopes, like the Vera Rubin Observatory, will dramatically improve our ability to find these elusive wanderers. Each interstellar visitor provides unique constraints on models of planetary system formation and evolution. The fact that all 3 objects were ejected from their birth systems indicates that planetary formation regularly produces excess materials that escape to interstellar space. The diversity of properties suggests that different stellar systems eject materials through various mechanisms, and that these objects undergo different evolutionary processes during their interstellar journeys. The time intervals between discoveries of interstellar objects may also provide statistical information about their abundance and the efficiency of current detection methods. The 8-year gap between Oumuamua and Borisov, followed by the 6-year interval before 3I/Atlas, suggests detection rates consistent with theoretical predictions for objects of these sizes and activity levels. Comparing the 3 visitors also reveals how observational capabilities have evolved during the brief span of their discoveries. The Oumuamua was detected and studied primarily through its reflected sunlight, with limited opportunities for detailed compositional analysis due to its inactive nature and rapid departure. Borisov enabled more comprehensive study through its prominent coma and predictable comet-like behavior. 3/A Tellus benefits from the most advanced observational techniques and longest advance warning, allowing coordinated campaigns involving space-based and ground-based telescopes operating across the electromagnetic spectrum. The lessons learned from studying the previous 2 visitors have informed the observational strategies applied to 3I/A Tellus, maximizing the scientific return from this rare opportunity. The study of these interstellar siblings contributes to broader questions about the structure and evolution of the galaxy as a whole. The chemical compositions, ages, and orbital properties of interstellar objects provide direct samples of materials from distant regions of the galactic disk, offering insights into stellar formation processes and chemical evolution that would be difficult to obtain through traditional astronomical observations. Future discoveries of additional interstellar objects will gradually build a more complete picture of the population of wanderers moving between stellar systems. Each new detection will add to our understanding of planetary formation processes, stellar system evolution, and the mechanisms that transport materials across galactic distances. The cosmic family of interstellar visitors will continue growing as survey capabilities improve and more sensitive telescopes come online. The three confirmed interstellar objects discovered to date represent pioneering explorers in our systematic study of materials from alien worlds. Ufumawama established that such objects exist and can be detected with current technology. Borisov demonstrated that some interstellar materials behave according to familiar physical principles. 3I/A reveals the extraordinary diversity that exists among these cosmic wanderers and the extreme processes that can accelerate objects to interstellar velocities. Together, these siblings from other stars provide our first direct contact with matter that formed around distant suns and traveled across the vast emptiness of interstellar space to reach our cosmic neighborhood. Each carries within its structure and composition a record of conditions that prevailed in alien stellar systems, offering unprecedented opportunities to study the diversity of planetary formation environments throughout the galaxy. As we continue to observe and analyze these remarkable visitors, we are building the foundation for a new branch of astronomy that studies the galaxy through direct samples rather than distant observations. The interstellar object family will undoubtedly grow in coming years, providing increasingly detailed insights into the cosmic processes that shape matter and transport information across the vast scales of galactic space and time. Why do some comets glow with an ethereal green light as they approach the sun, while others remain predominantly white or blue in their celestial display? For 3I/Atlas, this question has taken on particular significance as recent observations suggest our interstellar visitor may be undergoing a gradual transformation from its initial pale appearance to a distinctive green hue that speaks to fundamental chemistry occurring within its expanding coma. The phenomenon of green comets represents one of the most visually striking examples of how astronomical observations can reveal the invisible chemical processes operating in space. This coloration does not result from reflection of sunlight, like the colors we see in terrestrial landscapes, but rather from the emission of specific wavelengths of light by gas molecules that have been energized by solar radiation and other cosmic influences. The green color characteristic of some comets arises primarily from diatomic carbon molecules, designated C dice in chemical notation, that form when larger carbon-bearing compounds are broken down by solar ultraviolet radiation and other high-energy processes. These carbon dimers exist only briefly in the harsh environment of space before being further dissociated, but during their fleeting existence, they emit light at a wavelength of approximately 516 nanometers, corresponding to the green portion of the visible spectrum. Understanding the formation of diatomic carbon in cometary environments requires us to consider the complex photochemistry that occurs as solar radiation interacts with the diverse molecular species escaping from comet nuclei. Ultraviolet photons from the sun possess sufficient energy to break the chemical bonds in larger organic molecules, creating a cascade of reactions that produce smaller molecular fragments, atoms, and ions. For 3I/ADLs, with its unusual composition dominated by carbon dioxide rather than water, the pathways leading to diatomic carbon formation may differ significantly from those operating in typical solar system comets. The high CO2 content provides an abundant source of carbon atoms that can combine to form C-dot molecules under appropriate conditions. The specific chemistry involved depends on the exact mix of parent molecules present in the nucleus and the relative rates of sublimation as solar heating intensifies. The detection of green coloration in 3I/Atlas began subtly, appearing first in sensitive spectroscopic observations that revealed the characteristic emission lines of diatomic carbon superimposed on the comet's reflected sunlight spectrum. These initial detections required careful analysis to separate the weak emission signals from the much brighter background of scattered solar radiation, demonstrating the sophisticated techniques that modern astronomy employs to extract information from faint celestial objects. As 3I/Atlas has approached closer to the Sun, the intensity of the green emission has gradually increased, suggesting that the production rate of diatomic carbon molecules is accelerating with increasing solar heating. This temporal evolution provides insights into the thermal structure of the comet's nucleus and the depth distribution of carbon-bearing materials within the subsurface layers that feed the ongoing sublimation processes. The spatial distribution of green emission within 3I/Atlas's coma also reveals information about the physical processes governing molecular formation and destruction. Diatomic carbon molecules form most efficiently in regions where solar radiation is intense enough to dissociate parent compounds, but not so intense as to immediately destroy the newly formed CETHAS molecules. This creates a characteristic shell-like structure in the green emission that appears at a specific distance from the nucleus. Imaging observations using filters that isolate the green emission wavelengths show this shell structure clearly, with the brightest green regions appearing in a ring around the nucleus rather than being concentrated at the center where the highest densities of parent molecules exist. This spatial pattern provides direct evidence of the photochemical processes that create and destroy diatomic carbon in the cometary environment. The physics underlying this green emission involves electronic transitions within the diatomic carbon molecules that occur when they absorb solar radiation or energy from other sources. The absorbed energy promotes electrons to higher energy levels within the molecule, creating an unstable excited state that quickly relaxes by emitting light at specific wavelengths determined by the molecular structure and quantum mechanical selection rules. The lifetime of excited diatomic carbon molecules in the low-density environment of cometary comas allows them to emit their characteristic green light before being collisionally de-excited or further dissociated. This process, known as fluorescence, operates efficiently in the near vacuum conditions of space, where molecular collisions are rare and radiative transitions dominate the relaxation of excited electronic states. Temperature measurements of the green emitting regions provide additional insights into the energetics of the photochemical processes creating diatomic carbon. The rotational and vibrational excitation of sea-like molecules reflects the energy balance between formation processes, solar heating, and radiative cooling. These temperature determinations require sophisticated spectroscopic analysis of the detailed line profiles within the green emission bands. The observation of green coloration in 3I/Atlas also enables comparisons with the extensive database of green comet observations accumulated over decades of cometary astronomy. Most green comets are relatively young objects, making their first or early passages through the inner solar system when volatile materials remain abundant near their surfaces and can readily undergo the photochemical processing that creates diatomic carbon. Long period comets from the Oort cloud frequently display prominent green coloration during their first approaches to the Sun, while short period comets that have made many previous passages tend to show less green emission due to depletion of carbon-rich materials from their surface layers. The appearance of green coloration in 3I/ATLSI, despite its ancient age and long interstellar journey, suggests that its nucleus contains substantial reservoirs of carbon-bearing compounds that have been preserved during billions of years of cosmic exposure. The development of green coloration in 3I/Atlas may also be influenced by the unique conditions of its interstellar journey. Cosmic ray bombardment over billions of years could have created complex organic compounds through radiation-induced chemistry, providing additional sources of carbon that can be mobilized as solar heating penetrates deeper into the nucleus during the current passage through our solar system. Laboratory studies of organic compounds subjected to conditions simulating interstellar space have revealed the formation of complex carbon-rich residues that could contribute to diatomic carbon production when heated. These laboratory analogs help interpret the observational data from 3I/Atlas by providing insights into the chemical pathways that might be operating within the comet's nucleus and coma. The timing of the green transformation in 3I/Atlas correlates with other indicators of increasing activity as the comet approaches perihelion. Measurements of gas production rates, dust emission, and coma expansion all show similar trends toward higher activity levels, suggesting that the green coloration reflects the overall awakening of the nucleus as solar heating intensifies. Spectroscopic monitoring of the green emission also reveals periodic variations that correlate with the comet's rotation period, indicating that different regions of the nucleus contribute unequally to diatomic carbon production. These variations provide information about the heterogeneous distribution of carbon-bearing materials within the nucleus and the varying degrees of solar illumination experienced by different surface regions. The intensity ratios between green emission and other spectroscopic features enable astronomers to constrain the relative abundances of different parent molecules within the nucleus. Comparing the strength of C-this emission with that of CN, C-this and other carbon-bearing species provides insights into the composition and processing history of the carbon reservoir that feeds these photochemical reactions. Advanced imaging techniques reveal additional structure within the green emitting regions, including jets and streamers that trace the complex gas dynamics within the expanding coma. These features show how diatomic carbon molecules move away from their formation regions under the influence of solar radiation pressure and gas expansion, creating intricate patterns that evolve over timescales of hours to days. The polarization properties of the green light emitted by 3I/Atlas provide further insights into the molecular orientation and collision processes within the coma. Partially polarized emission indicates preferential molecular alignments that result from the anisotropic radiation field near the nucleus and the directional nature of the gas expansion processes. Ultraviolet observations complementing the visible light detection of green emission reveal the parent molecules and photodissociation processes that ultimately lead to diatomic carbon formation. The UV spectra show absorption features corresponding to larger carbon-bearing compounds that serve as the source material for the observed CTHO emission. The green transformation of 3I/Atlas also has implications for understanding the broader population of interstellar objects and their chemical evolution during passage through stellar systems. If other ancient interstellar comets similarly contain preserved reservoirs of carbon-rich materials, green coloration might serve as a diagnostic tool for identifying and studying these rare visitors. Theoretical models of cometary photochemistry are being refined to account for the unusual composition and history of 3I/A Tellus, incorporating the effects of cosmic ray processing during interstellar travel and the distinctive carbon dioxide dominated volatile inventory. These models help predict the evolution of green emission as the comet continues its approach to perihelion. The documentation of green coloration in 3Y/Atlas contributes to the broader understanding of how chemical information is preserved and revealed during cometary activation. The molecules responsible for this emission carry signatures of formation processes that operated in distant stellar systems, providing direct chemical evidence of conditions that prevailed in alien planetary formation environments. As 3I/ATOS continues its journey toward closest solar approach, the green transformation will likely intensify, providing increasingly detailed opportunities to study the chemistry of truly ancient materials under the influence of our sun's radiation. Each photon of green light carries information about molecular processes that connect this visitor to its origins in distant regions of the galaxy, creating a visible link between our solar system and the cosmic chemistry that operates throughout the universe. The green glow of 3I/Atlas serves as a reminder that color in astronomical objects often reveals far more than mere aesthetic beauty. In this case, the ethereal green light provides direct evidence of chemical processes that have been triggered by the interaction between ancient interstellar materials and the energy of our sun, creating a visible manifestation of the complex chemistry that governs the behavior of matter throughout the cosmos. In the cosmic theater of our solar system, every performance must eventually end, and for 3I/Atlas, the final curtain approaches with the same mathematical certainty that governed its initial arrival. This ancient traveler, having briefly awakened from its billion-year slumber to display the magnificent spectacle of its activated coma and tail, will gradually fade from our instruments and return to the eternal darkness between the stars, never again to grace any telescope with its reflected light. The departure of 3I/Atlas carries a poignancy unique to astronomical phenomena, for unlike the familiar comets that return to our skies on predictable schedules, this visitor embarks on a journey that will carry it beyond all possibility of future observation. The hyperbolic nature of its trajectory ensures that after its passage around the Sun, it will continue outward with sufficient velocity to escape our solar system entirely, joining the sparse population of objects that drift through the galactic void. Understanding the timeline of this departure requires precise calculations that account for every gravitational influence along the comet's outbound path. Following its perihelion passage on October 29th, 2025, 3I/ATLS will begin the long journey away from our Sun, gradually cooling as solar distance increases and the processes that created its spectacular display slowly diminish. The coma will contract, the tail will fade, and the nucleus will return to the dormant state it maintained during its billion-year journey through interstellar space. The final major gravitational encounter occurs during the comet's passage near Jupiter in March 2026, when the giant planet's immense mass will provide a parting gift in the form of additional velocity. This gravitational slingshot effect will accelerate 3I/ATLAS by several kilometers per second, ensuring that it departs our solar system even faster than it arrived. The precise amount of this acceleration depends on the detailed geometry of the encounter, but current calculations suggest a final departure velocity approaching 65 kilometers per second relative to the Sun. Observational programs worldwide were coordinating their efforts to capture the last measurable signals from 3I/ATLAS as it recedes into the outer reaches of our solar system. The brightness of the comet depends on both its distance from the Sun, which affects its internal activity level, and its distance from Earth, which determines how much light reaches our telescopes. As both of these distances increase during the departure phase, the object will become progressively fainter until it drops below the detection thresholds of even our most sensitive instruments. Current projections suggest that 3I/ATLAS will remain observable to large professional telescopes until late 2026 or early 2027, depending on how quickly its activity level decreases as solar heating diminishes. The exact timeline depends on poorly understood factors such as the thermal properties of the nucleus, the depth distribution of volatile materials, and the efficiency of various sublimation processes at low temperatures. The final detection of 3I/ATLAS will likely occur at one of the world's largest optical telescopes, using integration times of many hours to collect enough photons to distinguish the comet from the background sky noise. This last observation will mark the end of humanity's direct contact with materials that formed around a distant star billions of years before our Earth existed. After that moment, 3I/ATLAS will continue its journey in complete isolation, carrying its ancient chemical signatures back into the cosmic darkness from which it emerged. The trajectory calculations that predict the comet's post-solar system path reveal a destination that stretches imagination. 3I/ATLAS will spend tens of thousands of years crossing the outer boundary of our solar system, gradually escaping the Sun's gravitational influence as it travels through the heliopause and into true interstellar space. The exact timeline for this transition depends on how we define the solar system's edge, but even the most conservative estimates place complete escape within 50,000 years. Once in interstellar space, 3I/ATLS will begin another chapter of cosmic wandering that could last for billions of years. Statistical analyses of its likely trajectory suggest the comet will move through regions of the galaxy dominated by the thick disk stellar population, possibly encountering other stellar systems over geological timescales. However, the vast emptiness of interstellar space makes close approaches to other stars extremely rare events. The probability calculations for future stellar encounters reveal the almost incomprehensible scales involved in galactic dynamics. Even traveling at 65 kilometers per second, 3I/A Talas would require millions of years to traverse the distance to the nearest stars. The random motion of stellar systems through the galaxy means that close encounters occur only through remarkable coincidences of position and timing that play out over cosmic ages. During its renewed journey through interstellar space, 3I/Athelas will experience conditions that slowly modify its structure and composition over millions of years. Cosmic ray bombardment will continue the radiation processing that occurred during its previous interstellar transit, potentially altering surface chemistry and creating new organic compounds. Collisions with interstellar dust grains will gradually erode the nucleus, though at rates so slow that significant changes require millions of years. The thermal environment of interstellar space will eventually cool the nucleus to temperatures only a few degrees above absolute zero, freezing any remaining volatile materials into inactive states. This deep freeze will preserve the comet's remaining materials in conditions even more extreme than those it experienced during its previous billion-year journey, creating a natural laboratory for studying how matter behaves under the most extreme conditions in the universe. The magnetic fields that permeate interstellar space will also influence the comet's long-term evolution, though these effects remain poorly understood. Charged particles trapped in these fields may interact with any residual magnetic properties of the nucleus, while the fields themselves could guide the paths of ions created by cosmic ray impacts. These subtle interactions accumulate over vast timescales, potentially influencing the object's trajectory and physical properties. The silence that will envelop 3I/Atlas after its departure from our observational reach represents more than mere invisibility. This silence embodies the fundamental isolation that characterizes objects traveling through interstellar space, separated from all warmth, light, and gravitational companionship by distances that render them effectively alone in the universe. The comet will continue its existence in this state of cosmic solitude for periods that dwarf the entire history of life on Earth. Yet this silence also carries a profound dignity. 3I/ATLAS will become a permanent ambassador from our solar system, carrying with it the subtle gravitational and chemical modifications imparted during its passage through our cosmic neighborhood. Future civilizations that might exist around distant stars billions of years from now could in principle study these signatures to learn about the conditions that prevailed in our solar system during the 21st century. The departure of 3I/Atlas also marks the end of a unique scientific opportunity that will not be repeated in our lifetimes. Each interstellar visitor provides an irreplaceable sample of materials and processes from distant stellar systems, and the loss of observational contact represents the closing of a window into cosmic environments that we cannot study through any other means. The data collected during the comet's passage will be analyzed for decades to come, but no additional observations will ever be possible. The records and images captured during 3I/AT-LAS's visit will serve as permanent documentation of humanity's encounter with this ancient wanderer. These observations represent not just scientific data, but historical artifacts that preserve the moment when our species made direct contact with materials from another star system. Future generations will view these records as evidence of the cosmic connections that link our solar system to the broader galactic environment. The emotional impact of 3I/Atlas's departure reflects the human tendency to form connections even with inanimate objects that have traveled from impossibly distant places and times. This comet has become a tangible representative of the universe beyond our solar system, and its departure creates a sense of loss that transcends mere scientific regret. We are bidding farewell to a messenger that connected us, however briefly, to the vast cosmos that exists beyond our everyday experience. As telescopes worldwide prepare for their final observations of 3I/AT-LAS, the astronomical community faces the reality that such encounters represent rare gifts that must be treasured and studied with maximum intensity during their brief availability. The techniques developed and lessons learned from this visitor will prove invaluable when future interstellar objects grace our solar system with their presence, but each encounter remains unique and irreplaceable. The philosophical implications of permanent departure on cosmic scales challenge our human centered perspective on time and relationship. 3I/AT-LAS existed for billions of years before our planet formed and will continue traveling through space long after our sun burns out. Yet our brief encounter with it spans only the tiniest fraction of its existence. This temporal disparity places our observations in the broader context of cosmic evolution and the fleeting nature of all astronomical phenomena from human perspectives. The mathematical certainty of 3I/AT-LAS's trajectory provides no comfort for the finality of its departure. Unlike human farewells that carry possibilities of reunion, the laws of physics ensure that this separation is absolute and eternal. The comet's path carries it away from all possibility of future observation, making our current moment of contact precious beyond measure. In contemplating the departure of 3I/Atlas, we confront the fundamental loneliness that characterizes existence on cosmic scales. Objects separated by interstellar distances exist in effective isolation from one another, connected only by the universal forces that govern all matter and energy. The brief intersection of our solar system with this ancient traveler represents a rare moment of cosmic companionship in an otherwise vast and empty universe. As 3I/Atlas fades from our telescopes and returns to the darkness between stars, it carries with it our hopes and curiosity about the universe beyond our immediate cosmic neighborhood. Its departure reminds us that we exist in a dynamic galaxy where objects constantly move between stellar systems, carrying information and materials across distances that challenge comprehension. The silence that follows its passage is not empty, but full of possibility, for somewhere in that darkness, other ancient wanderers are beginning their own journeys toward distant encounters that may someday bring them to solar systems we cannot even imagine. December 19th, 2025, As Earth reaches its closest approach to 3I/A Talas, telescopes around the world capture what may be their final detailed observations of this messenger from deep time. In observatories from Chile's Atacama Desert to Hawaii's volcanic peaks, astronomers work through the night to extract every possible photon from an object that has traveled farther and longer than any previous visitor to our solar system. These observations represent the culmination of humanity's first comprehensive study of materials from the ancient galaxy, and the insights they provide will reshape our understanding of cosmic evolution for generations to come. The story told by 3I/Aslas extends far beyond the narrative of a single object's journey through space and time. Within its chemical composition, physical structure, and orbital characteristics lies encoded information about processes that operated when the universe was less than half its current age. The carbon dioxide ice that dominates its nucleus formed in stellar environments that no longer exist, while the isotopic ratios preserved in its ancient materials provide direct evidence of nucleosynthesis that occurred in massive stars that died before our sun was born. These chemical signatures serve as temporal markers that connect our present observations to specific epochs of galactic evolution. The enhanced carbon-13 ratios detected in 3I/A Talas's coma gases point to formation during periods when the galaxy's chemical composition differed significantly from current conditions. The lower abundances of heavy elements reflect an era when fewer generations of stars had completed their evolutionary cycles, enriching the interstellar medium with the products of nuclear fusion and supernova explosions. The implications for understanding early solar system formation emerge from these chemical contrasts. Our solar system formed in a galactic environment that had been enriched by billions of years of stellar evolution, providing the heavy elements necessary for rocky planet formation and the complex chemistry that eventually led to life. 3I/Atlas samples conditions from an earlier era when planetary systems formed with different raw materials and under different physical conditions. The extreme velocity and hyperbolic trajectory of 3I/Atlas also reveal information about the dynamic processes that shape galactic structure over cosmic time. The gravitational interactions that accelerated this object to interstellar speeds operated during the galaxy's more chaotic youth, when stellar encounters were more frequent and planetary system formation occurred in more turbulent environments. The survival of such high-velocity objects provides evidence for the violent processes that characterized early galactic evolution. Studying 3I/Atlas has also advanced our understanding of how materials preserve information during journeys through interstellar space. The cosmic ray bombardment, temperature cycling, and magnetic field interactions experienced during billions of years of interstellar travel create subtle modifications that can be read like pages in a cosmic history book. These processes operate so slowly that their effects accumulate only over geological timescales, creating records of galactic environmental conditions that cannot be obtained through any other means. The preservation of volatile compounds in 3I/A despite its extreme age, demonstrates the remarkable stability that materials can achieve in the cold vacuum of interstellar space. The carbon dioxide, carbon monoxide, and complex organic molecules detected in its coma survived billion-year journeys at temperatures only slightly above absolute zero, maintaining their chemical identities across distances that span significant fractions of our galaxy's diameter. These preservation mechanisms have implications for astrobiology and the possibility of life existing beyond our solar system. If complex organic molecules can survive interstellar transport over such vast timescales, then the chemical building blocks of life may be distributed throughout the galaxy by processes similar to those that delivered 3I/Atlas to our cosmic neighborhood. The comet serves as a demonstration that materials from one stellar system can reach others, potentially carrying the chemical prerequisites for life across interstellar distances. The observational techniques developed for studying 3I/Atlas represent significant advances in our ability to characterize faint, distant objects moving rapidly through space. The coordination between ground based and space based telescopes, the sophisticated data analysis methods used to extract information from limited photon counts, and the theoretical models developed to interpret complex chemical signatures all contribute to a new paradigm for interstellar object studies that will prove invaluable for future discoveries. These methodological advances position astronomy to take advantage of the increasing rate of interstellar object discoveries expected in coming decades. Next generation survey telescopes will detect objects like 3I/ATLAs while they remain much more distant, providing longer observational baselines and opportunities for more detailed study. The lessons learned from our current visitor establish the foundation for a new branch of astronomy focused on direct samples from other stellar systems. The statistical implications of detecting three interstellar objects within less than a decade suggest that such visitors may be more common than previously thought. If the current detection rate reflects the true abundance of interstellar materials, then our solar system may be continuously bathed in a gentle rain of objects from distant stellar systems, most too small or inactive to detect with current technology. This realization connects our solar system to the broader galactic ecosystem in ways that previous generations of astronomers could not have imagined. Rather than existing in isolation within our stellar bubble, we participate in a dynamic network of material exchange that operates across galactic scales and connects stellar systems separated by vast distances and timescales. The age of 3I/Atlas, estimated at 7 to 11 billion years, places its formation during the epoch when thick disk stars dominated galactic structure and star formation proceeded under very different conditions than those operating today. This temporal connection allows us to study directly the materials and processes that characterize the galaxy's formative period, providing ground truth for models of galactic chemical evolution and stellar system formation. The philosophical implications of 3I/Atlas extend beyond its scientific value to touch fundamental questions about humanity's place in the cosmic order. This ancient visitor reminds us that we exist within a universe far older and more dynamic than our everyday experience suggests. The materials now sublimating from its nucleus began their cosmic journey when Earth was a lifeless ball of molten rock, and they will continue traveling through space long after our sun exhausts its nuclear fuel. This cosmic perspective challenges anthropocentric views of time and significance. The brief moment during which 3I/Atlas graced our solar system with its presence represents an infinitesimal fraction of its total existence. Yet this encounter provides our only opportunity to study materials that formed around stars we will never see in regions of space we will never visit. The privilege of this contact carries responsibilities to extract maximum scientific value from observations that can never be repeated. The departure of 3I/Atlas also serves as a reminder of the finite nature of all astronomical phenomena from human perspectives. Unlike terrestrial objects that remain available for repeated study, celestial visitors operate according to cosmic schedules that offer brief windows of opportunity separated by vast intervals of absence. This temporal asymmetry places unique value on each observation and demands that we develop technologies and techniques capable of rapid response to unexpected discoveries. The legacy of studying 3I/Atlas will influence astronomy long after the comet disappears from our telescopes. The chemical analyses will provide reference standards for interpreting future interstellar object compositions, while the dynamical studies will inform models of how materials move between stellar systems throughout the galaxy. The observational techniques developed will establish protocols for studying similar objects, and the theoretical insights will guide investigations of galactic evolution and planetary system formation. Perhaps most importantly, 3I/Atlas has demonstrated that direct study of materials from other stellar systems lies within the capabilities of current technology. This realization opens new avenues for exploring questions about the prevalence of planetary systems, the diversity of chemical environments throughout the galaxy, and the mechanisms that transport materials across interstellar distances. The interdisciplinary nature of interstellar object studies also exemplifies the broader trends in modern astronomy, where insights emerge from combining observations across multiple wavelengths, theoretical modeling of complex physical processes, and laboratory studies of relevant materials under simulated space conditions. The study of 3I/ATLAS required expertise spanning orbital mechanics, spectroscopy, photochemistry, galactic dynamics, and statistical analysis, demonstrating the collaborative nature of cutting-edge astronomical research. Looking toward the future, the lessons learned from 3I/Atlas will inform strategies for studying additional interstellar visitors and for developing dedicated missions to intercept such objects during their solar system passages. The technical challenges of reaching rapidly moving targets on hyperbolic trajectories push the boundaries of current spacecraft capabilities, but the scientific rewards justify ambitious mission concepts that could provide detailed in situ measurements of interstellar materials. The cosmic story told by 3I/Atlas ultimately connects our local observations to the grandest scales of space and time. This ancient wanderer carries within its structure the memory of stellar processes that operated before our planet existed, chemical signatures that record conditions in distant regions of the galaxy, and dynamical properties that reflect the violent interactions that shaped early planetary systems. As we watch 3I/Atlas fade from our telescopes and return to the darkness between stars, we carry with us new appreciation for the deep time that underlies all cosmic phenomena and the remarkable connections that link our solar system to environments we can study only through such rare visitors. The ancient light reflected from its nucleus during its brief passage through our cosmic neighborhood has illuminated fundamental aspects of how the universe evolved from its early chemical simplicity to the complex dynamic system we observe today. The silence that follows 3I/Atlas's departure is not empty but pregnant with possibility. Somewhere in the vast spaces between stars, other ancient wanderers are beginning journeys that may bring them to our solar system in decades or centuries to come, carrying new stories of distant worlds and forgotten epochs. Our encounter with 3I/Atlas has prepared us to recognize and study these future visitors, ensuring that each brief contact contributes to our growing understanding of the cosmic processes that shape matter and information throughout the universe. In the end, 3I/Atlas teaches us that astronomy is fundamentally an exercise in cosmic archaeology, where we use present observations to reconstruct past conditions and predict future evolution. This ancient visitor provided a rare opportunity to hold in our telescopes a tangible piece of the early galaxy, connecting us across impossible distances of space and time to the cosmic processes that created the universe we inhabit. The insights gained from this encounter will endure long after the comet itself has vanished into the cosmic dark, contributing to humanity's eternal quest to understand our place in the vast and ancient cosmos.